Hi, and welcome to my first lab for Physics 2211 about constant velocity. I'm Matthew Erickson. So for an introduction, the purpose of this lab is to observe the motion of some object that is moving at a constant speed without changing direction. And we're going to compare the movement of a pushed object on a table to a computational model of that same object created with glow scripts. Some assumptions here is that there's no air resistance, no friction, normal force is equal to the gravitational force, and there's no displacement along the x-axis, or there is displacement along the x-axis, no displacement along the y and z axes. So for some fundamental principles of this lab is Newton's first law, which is an object at rest or motion will stay at rest or continue in motion in a straight line unless acted upon by an external force. Newton's second law is the rate of change of momentum of a body over time is directly proportional to the force applied, which correlates with the equation F equals ma. The position update formula is final position is equal to initial position plus velocity times delta t. And the velocity update formula is final velocity is equal to initial velocity plus the net force divided by mass times delta t. So for the experiment setup, we have a rolling object. In this case, it's tape, which is going to be our system. The surroundings external to the system are friction, gravity, and applied force. For our initial condition, we're going to use position equals 0 meters, and the glow script is going to be used for the computational trial. All right, so here is our video. As you can see, it rolls at a relatively constant speed from left to right across the screen. And the key thing here to notice is this little graph on the top right corner, which shows position over time. And as you can see, it's relatively linear, and that's what we want because the derivative of this would be velocity, and velocity should be constant. So some data from the tracker analysis is the tape roll diameter is 0.085 meters. It's not really relevant to our calculation. The video is in 30 FPS, which is helpful for calculating our delta t. The initial position is 6.196 e to the negative 3, which is a really small number, so we're going to approximate that to 000 meters vector. The initial velocity divided by the average velocity is 0.52500 vector. The initial conditions of a computational model, the mass of the ball equals 0.27, position equals 000 vector, and the velocity equals 0.5 vector, 0 vector. We got all these from the last thing. The initial time is 0, and the delta t is 0.03, and that's what we get from the frames per second. So for our calculation loop, as you can see, the zero net force vector, we use the velocity update formula and the position update formula. Then we update delta t, plot everything, and then print the position. And we do this for a loop of 1.78. So here's one of the key takeaways is the observed tracker versus the predicted computational tracker. As you can see, the red line here is the computed tracker, and our blue line is the tracker that we got from our video. As you can see, the computational one is very straight and flat, whereas the blue one is kind of like tapers off, and that's because of the error in our system, such as the friction or other human error. Discussion follow-up questions. What if you were to flip the axes? How would your results change? Basically, rolling the tapes to the right made the time and the position proportional. Where if you were to flip it, they would be negatively correlated. However, the overall results would not change from this lab because it's just the magnitudes would still be the same of the velocities. It would just be the direction that changes. For the other discussion follow-up questions, what do our observations mean? How many pushes and pulls forces are on the system? It's not necessarily possible to pinpoint exactly how many pushes or pulls are at play to give zero net force, because in this experiment, pushing a rolling tape across a table in hopes of achieving constant velocity, but there can be other things such like friction. We cannot achieve total constant velocity unless we have like a motor or something in a car. Sources of error could be human error, glow script, tracker miscues, or surrounding forces, such as friction. And that's it. Thank you for watching.